In the last video, we learned about the full training algorithms of neural network, and you are now ready to put theory into action. It's time to build a neural network, and we will do it together in this video. Let's go ahead and get started. To build our first neural network, we are going to use TensorFlow Keras, which is a very simple tool for constructing a neural network. It's a high-level language. It's approachable, highly productive interface for solving the machine learning problems, especially for the deep learning problems. And the core data structure of Keras are mainly layers and models. There are two ways for us to construct a neural network. The first way is to use the sequential model, which is a simply linear stack of layers. And then for more complex architectures, we can use the functional API. And these architecture or these models we will cover later on. And in this course, we will use sequential models. And there are two things that we would like to go through first. One is the when to use the sequential model, and the other is how to use the sequential model. Firstly, a sequential model is appropriate for a plain set of layers, where each layer has exactly one input tensor and one output tensor, and then these layers are stacked together. However, this is not appropriate when our models and also our layers has multiple inputs or multiple outputs. And also, if we would like to share the layer, this is not appropriate as well. And finally, if we have a nonlinear topologies, we say, for example, residual connections, multi-branch models, sequential model is not appropriate as well. And then for all these cases, we need to use the functional API. There are two ways that we can create a sequential model. The first way is passing a list of layers to a sequential constructor. And then the second way is to use .add methods to incrementally set up the layers. Let's take a look on these two examples. First thing first, we just import the sequential model and import the dense layer. Just like what I mentioned before, the first way is to create a sequential constructor and then passing a list of layers into it. First of all, we use the sequential functions to create this sequential constructor object. And then we just put these list of layers into this sequential constructor. And here we have two layers. The first layer has two neurons and has the input shaped with three inputs. And then we have one output dense layer and with the sigmoid activation functions. And let's take a look on these. You can see that we have the dense layer into the first layer, and then we have the second layer that is the output layer, and then the output shape is 1, and then for this first layer, the output shape is 2. We have 3 inputs, 2 outputs, and then finally we have 1 output. Again, we can use the .add functions to construct similar neural network. First of all, we can create a sequential object, and then we can add each of the layers one by one by using this .add function. And we just similarly we add the first layer with two neurons, 2 outputs, and 3 inputs. And then we can also add, we stack another layers by .add functions, and we stack an output layer with 1 output, and then the activation function is defined by the sigmoid. So if we want the cell, you can see that the structure are exactly the same for these two methods. Let me provide you some contents on these output shapes and also these parameters. In the output shapes of each of the layers, the models expect that the input to have a batch size as the outermost dimension, that is the leftmost dimension. Therefore, you can see that a null value is assigned here for greater flexibility. That means we do not need to bother with the batch size. We just leave it as a null value. And then the second parameters of the output shape is simply equals to the number of neurons in the same layer. So for example, for this layer, we have 2 neurons. That means as a result, we will have 2 outputs. And for these layers, we have 1 neurons. That means we are going to have 1 output. So the second parameters of the output shapes are simply equals to the number of neurons in the same layer. And then for each of the layers, each of the dense layers, there's a number of parameters. In this case, the input size plus we can calculate by using the input size plus 1 times the number of neurons. Remember that the parameters include the weight and also the bias. As a result, we need to use plus 1 because of the bias. And then the input size, say for example, for the first one, the input size or the input shapes is 3. And then we have 2 number of neurons. So that is a 3 plus 1, that is plus the bias, times the number of neurons. As a result, we get 8 parameters in the first layer. And then in the second dense layer, the number of inputs that is coming from this output shape, that is 2. So 2 plus the bias and then times the neurons, times the outputs neuron, that is 1. So we got the parameter 3 by using these equations. Although there are 2 ways for us to construct a neural network with the use of TensorFlow Keras, very often we will use the sequential model. It's preferable mainly because it's useful to incrementally stack the layer with the docf functions and frequently print out the models with the use doc summary. And then by using these methods, these will enable us to monitor how the stack of layers are connected with each other, especially that is especially useful for very deep network architecture. What we've done so far is just 6 lines of code, and we just import the sequential model from Keras, TensorFlow, and then we just import the dense layer from TensorFlow Keras. And we create the sequential model object, and then we add 2 layers. The first layer with 2 neurons and 3 features as the inputs, that is 3 inputs. And then we have the second layers with 1 neuron as 1 output, and then sigmoid is the activation functions. And then of course, we just need to compile the neural network with the appropriate optimizer, with the appropriate loss functions, and also the evaluation metrics. Let's put this in actions to see how we can build this neural network. First of all, we just input the models and not input the layers. We are going to use the sequential models and we are going to use the dense layers. So the first 2 lines of code just import the appropriate library. And then we set up the sequential object and by assigning to a name called model. And then we add the first layer with the 2 neurons, 3 features from the inputs. And after that, we add in 1 more layers with 1 neurons, and then with the sigmoid activations output, with the sigmoid activations function. So here you can see that 3 features as the inputs, and in the first layer we have 2 neurons, and then in the second layer we have 1 neuron, and that is our output. that is a probability because you are using the sigmoid activation functions. And finally, we just need to compile with everything together. We need to define the optimizer. We will talk about it later on. Here, we just assume we are going to use the RMS pops, one of the optimizers that we can use. And then the other one is the binary cost entropy. This is mainly used for the sigmoid activation functions, and we will also let you know what kind of loss functions that we should pick up for what kind of outputs or for what kinds of problems that you are dealing with. And finally, we also need a evaluation metrics. In that case, we can continue to monitor the performance of our neural network. Now let's take a look on the details of each of the steps. In the step 3, we create a sequential model. Just like what I mentioned, Keras provides 2 ways for constructing a neural network. That is the sequential model and also functional API. But in these steps, if we are going to use the sequential models, an empty sequential model object is created. After creating this empty sequential model, we are ready to stack our layers by using the docx functions. In step 4 and step 5, in our example, we are going to add 2 layers. And then the first layer is with 2 neurons, 3 features as inputs. And then in the second layer with 1 neuron as the outputs and sigmoid as an activation function. Keras provides plenty of pre-built layers for different neural network architectures to tackle different types of deep learning problems. And there are plenty of layers that we can use, but I'm not going to go through them because later on in this course, you will come across most of these layers. And in this, but for the time being, we mainly use this dense layer, which is a core layer in the neural network architecture. It's a very standard neural network layer, and which is very helpful to produce outputs in the desired formats. And dense layers takes different parameters. Here are a few commonly used parameters. First of all, that we need to define the number of neurons, and that will determine the number of the outputs. And then we need to define the activation functions. By default, is a linear activation functions. Just like what in our example, we use the sigmoid activation function as the output layer. And then for the first layer, we also need to define the shape because the models need to know what kind of input shapes it should expect. For these reasons, the first layer in the sequential model needs to receive additional parameters about its input shape. And there are several possible ways to do this by passing an argument called the input dim, input dimensions, or the input shapes. And then in our example, we use the input shapes for this argument. And finally, once the neural network architecture is set up and added into the sequential model objects, the model can be compiled with the .compile function. This compile function is very powerful. It allows us to input for different parameters. And then the most important parameters include the optimizer, the loss functions, and also the metrics. Let's take a look on the logics behind. For the loss function, once the neural network architecture is set up and added into the sequential model object, samples are forward propagated and the corresponding estimates, that is the y hat, are calculated. You can see that the samples are passing to this neural network and passed into this sequential object. And then samples are forward propagated and the corresponding estimates are calculated. That is the y hat. And then loss function is then applied. Here you can see that the loss functions will compare this estimate with the labels taken out from the samples. That is the true value. So the So these loss functions applies to estimate the loss functions between the true value and also the predicted value, in order for us to see how bad our model is or how good our model is. So these loss functions will calculate these loss value between the estimate and also the true value. And based on these loss value, an optimizer is used. Optimizer is like a backward propagations, and it backward propagates and calculate the gradients with respect to two parameters, that is the W and also that is the B, which is the weight and also the bias respectively. And remember that the training will be stopped either when the maximum number of epoch is reached, or a monitor quantity that is early stopping functions has stopped improving. That means we try to overfit, we try to avoid the overfitting issues. Therefore, loss functions here is used for forward propagations. Forward propagations to calculate the loss. And then the optimizer here is used for backward propagation. That is used to calculate the gradients to update the parameters W and B to minimize these loss value. Finally, we have a matrix, which is an additional evaluation function that is to judge the performance of the models. Matrix functions are very similar to the loss function, except that the results from evaluating a matrix are not used when training the model. Therefore, any loss functions can also be used as a matrix, but however, these matrix is not going to use it when training the model. The main reasons for that is because it's difficult to judge the performance based on the loss value, such as the MSE, the mean square error, or the Wood mean squares error. Therefore, sometimes an extra matrix is for us to use, such as accuracy or the mean absolute error, for us to use to judge whether or not the performance of the model is good or is bad, something like that. And that is used for additional evaluation. And this is particularly useful when we need to judge whether the model is overfitted or underfitted. To tackle different types of the problems, we need to have different types of neural network architecture. Therefore, the combinations of output layers and activations, and also the loss functions, are particularly important. There are two main types of problems that neural network can address. One is the classifications, and the other one is the regressions. For classifications, there are three main types. The first is a binary output, that is 0 or 1. In this case, we will use sigmoid activation function to determine the output probability and then run off these probabilities to guess 0 or 1. And of course, for loss functions, because it's a binary output, we will simply apply binary cost entropy. For the second types of the problems, that is the single labels, multiple classes, it means that there are different classes, and we need to determine these labels belongs to which class. But remember that we only have one labels here, so it's just like a classifiers, and only one of these class is to be selected for each time. To ensure only one class is selected each time, we will apply a softmax activation functions. And also in the last layer, we will use the categorical cost entropy to train the models. And softmax will returns you a n dimensions vector with sum of all these elements equals to 1. And the one with maximum values is the predicted class. The third types of classifications problems is multiple labels and multiple class. In neural network, When single label is required, we will use a softmax layers as the last layers to learn single probability distributions that range over all the classes. In case where multiple labels, multiple class that is needed, we will use a multiple sigmoid on the last layers, and therefore each predicted class will have its own probability. And the one has the highest probability, it will be the predicted outputs. And in this case, because we're using the sigmoid functions, with the loss functions, we can continue to use the binary cost entropy. The other types of problems that neural network can address is regressions. And say, for example, if the output type is a numerical value between 0 to 1 instead of 0 or 1, that is between 0 to 1, that is a continuous numbers, and a sigmoid functions can be used, and because it will provide you a output value between 0 to 1. And in that case, we can also use the binary cost entropy as the loss functions, or mean square errors as the loss function. And finally, for the last types of regressions problems, if the output is a numerical values, instead of between 0 to 1, that could be any numerical value. And the output layers, by default, we can use the linear functions, linear activation functions. And of course, the loss functions, we can continue to use the mean squared error. And that's it for these videos and this series. In this video, you just learned how to build a neural network. I will upload this Jupyter notebook and you can download the notebook and go through it. When needed, you can refer to the YouTube videos or you can leave me a comment. I will try my best to help. I hope you enjoyed and learned something from this course. In this course, we also have a bonus exercise. Let's go through it together. See you in the next video. Bye-bye.